I'm Andrew Hanson from Indiana University. I'm going to be talking about matching paired sets of data, both translational data and orientation frame data. My name is Andy Hanson. I am from Indiana University. I'm supposed to be retired, but I have this incredibly seductive thing on my desk called Mathematica, which keeps getting me into trouble. And I'm going to tell you today about how I got into trouble about a year ago when my daughter, who's a biochemist, bioinformaticist involved in protein matching, said, "Please explain to me the Horn RMSD quaternion matching problem." After speaking to a number of people here at the last WTC, I gradually worked my way into a rather interesting set of solutions and new problems in the orientation matching problem. So I'm going to talk about paired data sets and paired data sets, I guess you can see that, are interesting for a lot of reasons. One is that the method I'm going to use requires quaternions, and I just happen to have written a 498-page book on quaternions, which has just been released in print on demand and ebook with all of the typos corrected after 12 years. So the typo corrected version of Visualizing Quaternions is available from Elsevier. More to the point, for the last half century, a set of problems involving matched objects, such as what we now know as GPS satellite tracking matching, photogrammetric matching in aerial reconnaissance, and more recently in matching a known crystallized protein to a simulated protein to see if you did a good job on the protein matching. It's very heavily used in bioinformatics for that purpose. And the 3D problem is the one that has been really used for problems like that for the last, well, since the 50s. And they have all involved numerical approximations. You can get exact algebraic solutions, but they're all basically involving four-dimensional, 4x4 matrices. And if you try to evaluate those symbolically in Mathematica, you get pages and pages of symbols that are relatively intractable. In fact, when I was here a year ago, I was actually having trouble with the two-dimensional subset, and I had to get Michael Trott to point me to a technique to get me out of that. And it went on from there to the point where today I am going to tell you how I have used quaternions and Mathematica to produce the first, I should include usable, exact algebraic solutions of the full 3D spectra and the 4D eigenspectra, and extensions to 3D and 4D orientation frames. A few caveats. Of course, there are algebraic formulas. The singular value decomposition and eigenvalue in Mathematica will produce both numerical and algebraic output, but they are hugely complex. In fact, I tried the four-dimensional problem for the singular value decomposition, and I wound up with 9 gigabytes of symbols. So the context into which I am diving here is I'm starting out with 9 gigabytes of symbols from evaluating one of the standard ways of solving this type of optimization problem, and I am going to show you one line. I'm going to show you a one-line solution. There is absolutely no obstacle for Felix Klein to have discovered this formula. If he did, I have not seen it. No one that I know has seen it. And if anyone in this room knows of a place where Felix Klein or someone in the 19th century wrote down this formula, I would be thrilled to find out about it, because that's only a third of what I've done. And so I'm not scared of discovering that formula, because there's more to do. Nevertheless, I'd certainly love to know if there is such a thing, because I have actually made extensions to the orientation frame problems, which are actually even better adapted to quaternions than the spatial problem that I will talk about now. Go the right way. So the basic problem of the root mean square deviation matching problem is you begin with a set of input data, and I refer, for example, to a set of protein carbon alpha locations in the PDB database. That's a good example of a reference data set, which we'll call Y. That's traditional in the literature. And one or more, maybe, if you've done 1,000 protein simulations, 1,000 things that are supposed to look like the thing in the PDB database, but you're not sure if it does. So the question is, how do you match your test data to see if it looks like the reference data? And the task becomes to pick a single rotation matrix that minimizes this object. That is, you start out with the sums of the squares of the distances between the two different data sets. You apply one single global rotation to each element of the test data set, and you want to find out what rotation matches those. It is assumed to start with that you have aligned the centers of mass. That's traditional in this problem. And then you go on from there. We will refine the problem from a minimization problem for the RMSD to drop some constants and turn it into an identical problem up to constants, which I call the cross-term measure, delta. And instead of minimizing the RMSD, we will maximize delta. Now look and see what the structure of delta is, and this is true for any dimension. This has no particular dimensional dependence until we get into the quaternion part of it. You wind up with the rotation operating on the test data dotted into the reference data, and so that Y in terms of multiplication moves over to the left. So this turns into essentially a trace of the rotation matrix times what's maybe known as the cross covariance matrix, and that has x on the left part and y on the right part. That's a matrix that's not symmetric, very definitely not symmetric, and so the raw form of the RMSD optimization task is to find the global rotation matrix R that minimizes that trace. All clear so far? Okay. Now, what it looks like, and this is just a two-dimensional sample. So if you start out with the reference data in red, and then a typical sort of simulated noisy data set like a protein simulation would give you the blue points as your test data. And then this is kind of where you start. This was where my simulation starts. And then I apply a global rotation, leaving the red points, the reference data where they are, and you can see that these red lines between the starting point and the reference and the rotation of the test data are now the individual pieces of the norm of x minus y. Okay, so what we're doing is we're summing the squares of all of the red lines. That is the intuition of what is going on here, and what we can see, let's see if I can do this right. You can actually do this. Let's see, this should be bigger. Can I magnify that? Hello? Listen to me? How about that? Yeah, okay, here we go. Okay, so this is just an example of how this works. You take an individual rotation matrix and you simply rotate the rotation matrix, and the cost, the whole score, the delta, is the blue curve. As I change the rotation matrix, pop, there's the optimum, overshoot, and it gets worse. So that is the problem. The problem is to find that point in the space of objects. Okay, so that's our objective. So what I'm going to talk about now is a quaternion version of the 3D version. What I just showed you was an example in 2 dimensions. That's very simple. And the interesting thing about this problem is that it was discovered independently in 3 different literatures photogrammetry, satellite matching, a whole bunch of literature from NASA research centers, and proteomics. And none of the 4 papers that I've found that claim to be original cites the other over a period of 50 years, again and again and again and again. I got acquainted with this when I was working at the Stanford Research Institute in the Artificial Intelligence Center with a consortium of universities working on machine vision. And one of my colleagues, Bertolt Horn, now retired from MIT, one of the grand old men of robotics and machine vision, was one of those four papers. And I knew of his work since the 80s. But there was another paper that preceded his that he didn't even know about, and several papers that followed that referred to neither the preceding paper nor Bertolt Horn's. The method that these 4 papers use reduces the 3D matching problem, which in fact can be solved in any dimension by singular value decomposition, which can be shown through an argument by a fellow named Kabsch, K-A-B-S-C-H, is equivalent to minimizing a Frobenius norm for the matrix. Those are equivalent. The SVD and the Frobenius norm are connected, or minimizing the Frobenius norm are connected. What Horn and the other folks did was to change the 3D problem to a 4-dimensional linear algebra problem involving a quaternion eigenvalue. And that particular problem is easy to solve by Newton's method, and that is the problem that is the method that has been used with the quaternion minimization for the last half century. I'm going to show how to exploit quaternions in Mathematica to solve this, what is in principle a very difficult cubic or quartic, depending upon which task I'm doing, algebraic problem. Okay, the problem is clear. Here's how it works. I start out with just a few basic facts about quaternions. It's a point on a 3-sphere in 4-dimensional Euclidean space. It's a 4-vector with norm 1. It obeys a multiplication rule, and the multiplication rule has the property that it is non-commutative. And because it's non-commutative, it turns out to be equivalent to multiplying SU2 matrices by SU2 matrices. SU2 is the covering group of the SO3 rotation space. So one can construct a bilinear product of quadratic form and quaternions that produces the rotation matrix. And if you replace R of Q in the trace of R dot E by this matrix, you can simply pull out a column of quaternions on the left and a column of quaternions on the right. So it translates this into, translates the trace into a quadratic form, and the maximum eigenvalue of this, since Q dot Q is equal to 1, is the maximum possible value of this measure. The matrix that appears itself appears because of that funny little non-commuting way in which the quaternions multiply, so that they group together in strange ways when you break out the Q left and Q right. This is the way they break out. It's a non-trivial, traceless combination of the data matrix E's. And just as a footnote, I will not have time, since I only have 10 minutes left, to tell you about this, but I've also solved this whole thing for a 4-dimensional problem in which this matrix has no constraints at all, traceful and non-symmetric. So what we do is we just look at the eigenvalue problem itself, take that matrix M with the EXX plus EYY plus EZZs, and evaluate its determinant in 2 ways. One is as a power series in the coefficients in E. So this is linear in E, quadratic, cubic, and that's the determinant, quartic in the data. But it also can be written as the product of the eigenvalues themselves, where we're looking for the maximum eigenvalue epsilon. These are essentially equivalent polynomials in E. And what you can do then is to observe that the polynomials are just numbers, because E comes from the specific locations in space. I resolve the previous set of two equations to eliminate the variable, the little e, and I see that the number e, the numbers p sub I of e are each a particular polynomial in the solutions. Therefore, our task is to invert this equation to find the eigenvalues. Again, you can do this just by typing into Mathematica, and you get kilobytes, megabytes, gigabytes, depending upon the particular variant of the problem. If you plug it all back into the equations I have, the eigenvalues are now replaced by the x, y's, and z's, of which they are linear combinations of square roots. So one of the things I've done here is I've essentially reduced the order of the thing that has to be solved by the solve function. So if you now plug these equations into solve, remember the trace is 0, so P1 is 0. It gives you 6 sets of solutions that have a very strange structure. The first elements are all relatively simple, and the other 2 elements of each of the solutions fill pages and pages of absolutely incomprehensible algebra. You look at it, you run simplify on it, you take a piece of it, you run simplify on it. Nothing you do works. Trust me, nothing. But there's a property. You look at one of the short ones, and it's not too bad, actually. It has a fairly simple structure. And the question is, what's the relationship of that structure to everything else? Well, what happens is, if you plug in random numbers, you find that each of the short things has a corresponding identical number in the 30 kilobyte things. So they're all the same. The 30 kilobyte things simplify in another sector of the solutions to the other things. You can put it together like a jigsaw puzzle and find the algebraic solutions all in the simple one-page form. That helps a lot. So if you now stare at those expressions, it turns out that all of those expressions break up into x, y, and p of this exact same form, basically r cosine minus p2, where the cosines correspond to the real parts of the cube roots of -1. That's all there is. The entire structure of this linear algebra problem involves the 3 cube roots of -1. The more complicated one, the 4-dimensional one, it's the complex roots, because they're complex roots in the 4 dimensions, non-symmetric. And so these wind up being e to the I 2 pi I k over 3. In the real case, in the symmetric case, everything's real, and so these are all basically real numbers with the +0, -2 pi over 3, +2 pi over 3, and the little functions that I have there are extremely simple. Just a few lines in P2, P3, and P4. You plug those into this, and you have not only your eigenvectors, but you have them in order. If you choose the right order of the little cosines on the previous page, that is your maximum eigenvalue. The problem is solved. You can pull out the eigenvectors just by solving this equation by plugging in epsilon1 for that variable e. You have to be a little bit careful if m has a diagonal element. And this is the point at which I can actually spend maybe 2 minutes running a demo. Let me just give the summary, then I'll run the demo. So the solution I just showed you is unknown to the best of my knowledge. It might be there in the 19th century literature. I haven't seen it. All the previous 20th century literature solves these numerically using Newton's method for a single maximum quaternion eigenvalue, giving the quaternion solution for the optimal alignment of the RMSD problem. Using similar methods, I have solved the 3D frame alignment problem, where for example, each protein, instead of a position, is a list of the orientation frames of the amino acids. And I've solved it in addition for 4 dimensions, which is an extension to a pair of quaternions a non-equal quaternions bracketing a generalized M function. Okay, so I have a couple of minutes left. Let me come down to here. Okay, so here is an example of a three-dimensional data set. So this is, and you can sort of see it's been rotated around that core. See that hole in the middle? That's a three-dimensional data set. Here is the alignment, moving from out of alignment to in alignment, using the optimal solution. And the last thing I want to do, oh yeah, and here's an entire set. So here are 1,000 different data sets. So I have pulled up 1,000 different data sets, and what I'm going to do is I am going to create the list of eigenvalues. So you can see that it says map eigenvalues onto the matrices. Did that evaluate? No, hold on, what happened? Shift return. There, okay. And then I'm going to do it with my function. And then this is it. This is the entire function that we evaluated. Let's compare the lists. Okay, so from Mathematica running list of eigenvalues. These are the list of maximum in order eigenvalues, and here is the comparable list from the algebraic form. And now I'm going to take all 1,000 elements of the eigenvalue list. I am going to subtract them. I'm going to tally them and chop them. And it's 0,000 within 10 to the minus 15th. Every single one of the algebraic ones matches the algebraic set. Thank you very much.